Let A be an n by n matrix with entries from a field F. We have seen the null space of A. We now see two additional vector spaces associated with the matrix A. The first one is called the column space of A, and is denoted by C of A. And the column space is formed by taking the span of the columns of A. So each column gives you a vector, and you take the span of all those vectors. Because each column is an M tuple, the column space of A is going to be a subspace of Fm. The second vector space that we are going to look at is the row space of A, and it's denoted by R of A, and is given by the column space of A transpose. So every vector is going to be an n tuple, and this is going to be a subspace of Fn. We now look at an example to see how we can compute a basis for the column space of A and a basis for the row space of A. And we're going to look at two cases. The first case is when the matrix is in reduced row echelon form. Let's take this matrix A. Say we want to find a basis for the row space. First, we take the A transpose, because the row space is given by the column space of A transpose. Clearly, we don't need this tuple of all zeros. And in order to span the column space of A transpose, we really need both columns here. Because the first column is the only one that has a non-zero in the first entry, and the second column is not a scalar multiple of the first column. So a basis is going to be given by just the first two columns. And in general, if you have any matrix A in reduced row echelon form, the non-zero columns of A transpose will give you a basis for the row space of A. Now let's find a basis for the column space of A. First, notice that the second column is minus 2 times the first column, and the fourth column is simply minus 1 times the first column plus the third column. So I can write both the second column and the fourth column of A as a linear combination of the first column and the third column of A. And so we don't need the second column and the fourth column in order to span the column space of A. But now if you look at the first and third column, they are linearly independent. So a basis is simply given by the first and third columns of A. And in general, for a matrix A in reduced row echelon form, the pivot columns will give you a basis for the column space of A. So let's look at the case when the matrix A is not in reduced row echelon form. Let A be an n by n matrix, not necessarily in reduced row echelon form. Now the key to find a basis for the row space of A is the following. Elementary row operations do not change the row space. What that means is, if I transform A to a matrix R using elementary row operations, then the row space of A and the row space of R are identical. How does this help us? What we can do is, we first transform A to a matrix R in reduced row echelon form using elementary row operations, and then apply our earlier results. We simply take the non-zero rows in R. Then the set of all these rows transposed will give you a basis for the row space of A. But what about the column space? Well, elementary row operations do change the column space. For example, if a matrix A is this, if you row reduce this, you end up with this matrix. And clearly, the two matrices do not have the same column space. But not all is lost here. The pivot columns in R precisely tell you which columns to pick in A to give you a basis for the column space of A. So, a basis for the column space of A is given by the columns of A corresponding to the pivot columns in R. So let me illustrate this with an example. Say A is 1, minus 2, 3, 1, 0, 1, minus 1, 0, minus 1, 1, minus 2, minus 1. And row reducing this matrix will give you 1, 0, 1, 1, 0, 1, minus 1, 0, and 0, 0, 0, 0. So the pivot columns are columns 1 and 2. And so these two columns will give me a basis for the column space of A. And in this case, it is not too difficult to see that column 3 can be written as a linear combination of the first two columns. What you do is you take A1 minus A2, so the first column of A minus the second column of A, and column 4 is simply column 1. Now notice that the number of vectors in the basis for the column space is precisely the number of pivots. And that's also true for basis for the row space. And so what I can write down is the dimension of the row space is equal to the dimension of the column space. And this value is called the rank of A. And it's usually denoted by rank open bracket A close bracket. So for the example up here, the rank is 2.